Now we're going to look at a concept called regularization, which will be very useful in not only making sure we don't overfit our models to our training data, but also in model selection. So we talked in the last video that it can become very unfeasible, especially as you have large numbers of features in your models, to try to go through every single possible model combination when choosing the best model. And so the idea behind regularization is, what if instead you use all the available features you have, but only a little bit? So what do I mean behind that? Let's imagine now that I'm taking each feature that we have and just use it a little in the model. So the notation here for our multiple linear regression model is what we've used so far, but I will say that instead of using x1 like I have been, I'm replacing it with phi to represent, like, maybe we've already done some feature transformations. Maybe these are our parameters squared or the log of our parameters. So I'm just leaving this more generic, that we've already done some feature engineering and now I want to fit the model. If we restrict how large each theta can be, then we are going to restrict how much each feature could contribute to the model. So you can imagine that if I end up fitting the model and I get a very small value for theta 1, then basically this feature, whatever this feature is barely going to impact the prediction, right? And so in that case, you could think of our model decreasing in complexity. If my theta 1 is super tiny, it basically means this feature barely matters. So in regularization, we are going to put a limit on the magnitudes of the model parameters. And in that process, basically force the model to select the best features or portions of the best features given the constraint. So for example, if I set a limit and I say that the sum of all the absolute values of the parameters can be no larger than some number, q. Think of me as like setting a budget. Think of this as the budget. At the end of the day, each of these parameters, their absolute value and the sum has to be restricted by this q. Then some parameters will need to be small, right? So that the sum remains below q, and it's going to help the model have to basically prioritize your parameters. Now, this is with a caveat. This assumes all of your features have the same scale, right? Like, what if one of your features is huge in the scale and another feature is teensy tiny in the scale? Well, then that will unfairly affect what these weights need to be. So before we do this regularization, we're actually going to standardize all of our features first. We'll put them into standard units, and then they're basically all in the same playing field. And then we'll let our optimization process basically decide mathematically which feature should get more weight than another. I'm going to help you visualize this first because I understand this can be conceptually challenging to wrap your head around. So here's a visual, and before we get too far in this, I want to relate this. We had been looking at mean squared errors. Let's call this theta 1 and theta 2 just to be consistent. This was, for example, our mean squared error function when we were doing simple linear regression. And the idea was we were trying to find the slope and intercept that give us the minimum mean squared error. Visually, what we're looking at in this picture right here is like a topo map or a contour map. We're looking downward, not on this exact function, but it's the idea that you're looking downward on some cost function. This one has the shape of kind of an ovally shaped bowl, and it's a valley, right? It's going down, and the minimum value occurs right here in the middle. I'm going to just show you one other demo in case these contour plots are not something you've seen before. This is basically a somewhat similar visualization as to what we saw in the slides. We just had color or shading instead of just the contours here. But really what this represents is in 3D, you have a function. I'm going to turn it around so you can see. You can imagine this being our mean squared error is this bowl like this shape. and I'm trying to find the minimum of this, so the minimum is going to occur there. And that's really what I'm looking at, like out of all the mean squared errors, which values of theta 1 and theta 2, or in this picture x and y, give me the minimum value on this bowl. So that's really what we're looking at. We're just looking at it head on, like that, right? We're seeing the circles, or the little ellipses in the case of our example, but it's basically representing this idea that you're trying to get to a minimum value on this surface. So back to our visual with no constraint, let's imagine this as being your optimal values for your parameters. That's where you'd have the minimum of that elliptical bowl. Now, when you apply a constraint, right, and so in the middle here, I'm just replacing the name of those optimal parameters. I'm calling it your optimal parameters without regularization. Think of regularization as us going and putting a restriction, we're adding a budget. If I have no regularization, it's the equivalent to having a very, very, very large queue. Just saying, you know what, I'm not going to put a limit on you. You don't have to restrict your spending. And in that case, well, let me back up. In that case, this would be my best theta. Okay. Now, let's assume now I'm going to apply a constraint. If I decide I want to make Q some value that's not so huge, here is an example of possible plot for Q. So this intercept here would be right at Q. And I'm basically saying I need the sum of the absolute values of my parameters to be less than or equal to Q, which will give me this sideways, or this kind of diamond shape. Now I am going to restrict what thetas I'm allowed to use. I can't get out here. I can move anywhere inside this restricted region. And in that case, under this constraint, the parameter that's going to bring us lowest in the valley, again, imagine that you're looking down, there's a valley, it's going down to the lowest point right here, but you're only allowed to walk on it in this region. So if you want to get to the lowest you can in this region, it ends up being right here, because this is the darker the blue, the lower the surface. So under this constraint, that would say, all right, here's the values of theta that I'm going to use. And notice what that means is I'd give theta 1 a value of 0. And so theta 2 would be the only value in my model. So you can see how this idea of regularization is going to make my model basically have to pick which parameters are more important, in a way. And then if you change the value of Q, right? So here, I'm making it smaller, and I still, in this picture, I still wouldn't include theta 1 in my model. I would include theta 2, but it wouldn't be able to have as much of a large value in front of it, right? It's still going to be somewhat limited. So what about if I move it like this, right? I made it a little bit bigger. So now my model would include both theta 1 and theta 2, but it's going to have a smaller coefficient for theta 1 and a larger coefficient for theta 2. So it's still kind of giving some priority to theta 2 in this process. So one thing I want you to think about is, how does the size of Q relate to model complexity? And I want you to answer between these two. Does it mean that smaller Q implies use more predictors in the model, or use less predictors in the model? Take a minute and think about that. Okay, so smaller Q is going to result in less predictors in the model. Your model is going to become simpler because you're basically restricting where your parameters can lie, and the name of this is going to correspond to increasing regularization. Think of regularization as kind of limiting your model, and so if I'm making it simpler, I'm putting more regulations on it. I'm not allowing it to go to the optimal minimum here. So smaller Q corresponds to a larger regularization and a simpler model. A large Q is going to correspond to less regularization, right? Because if I have a super large Q, if I had like something like this, well, then my optimal is going to be right here at the no regularization. I'll get to the minimum part of the valley. And again, you may be thinking, wait, what's wrong with the minimal part of the valley? I thought that's what we wanted. Yes, we do, but not on our training set, because if we do that on our training set, we can definitely overfit. The model doesn't know that we're trying to be able to generalize this to unseen data. And so if it's just trying to get to the bottom of the valley of your training set, it likely is going to overfit. And regularization dials it back a little bit to try to help it see the forest from the trees. It's trying to help the model see general trends and not get too bogged down in the details, trying to get to the very minimum for that particular data set. Again, when Q is very large, this corresponds to no regularization, or very small regularization. This essentially will have no effect. Okay, so in general, what we do in this process, though, is exclude the intercept from the constraint. So just let the intercept be on its own. This is to avoid a situation where we would always predict 0. So basically, if the model has very, very small q, it's essentially going to just result in the constant model. It'll basically just give you y is equal to whatever your intercept was, right? And so I don't want to also include the intercept, because then small q will just result in a 0 model, which is not useful at all. So I just restrict my parameters in front of my features, but not in front of my intercept. So this is a visualization behind this whole concept, and basically it's a way for us to try to find this sweet spot, right? Is to basically adjust our regularization. So over here on the left side of the situation is very high regularization, a simple model. I'm basically really limiting the number of parameters. And then as I move to less regularization, as I move to less regularization, smaller regularization, I get a much more complex model, but I can have some overfitting. So one of the questions that we're going to address, and we'll look at this in the next video, is how do we find the right amount of regularization? And if you're thinking, oh, we might be able to do this via cross-validation, you are correct. So in the next video, let's look at this in an actual example. We'll look at how we can fine-tune our hyperparameter that controls our regularization to get kind of our best sweet spot here.